So what did you guys let u equal? 3x? Okay. So then du was 3 dx. We need the dx. We don't need the 3. Move it on to the other side. So now we can rewrite our integral as the integral of sine of u times 1/3 du. Let's go ahead and change our bounds of integration. If x is pi over 12, then u is 3 times pi over 12, which would be pi over 4. If x is pi over 9, then we have 3 times pi over 9, which would be pi over 3. So changing our x's to u's really just made them easier to work with anyways, because we don't know much about sine and cosine at pi over 12 and pi over 9, but we do know about pi over 3 and pi over 4. The antiderivative of sine of u would be what? Negative cosine of u. I'm going to leave that constant of integration 1/3 out. And I'm going to evaluate that from u equals pi over 4 to pi over 3. In fact, I'm going to even go ahead and pull out the negative, because it's also like a constant, right? So I have negative 1/3 times cosine of pi over 3 is 1/2. Good. Minus cosine of pi over 4 is root 2 over 2. That's the easier one to work with. So I have negative 1/3 times 1 minus the square root of 2 over 2 would be negative 1 plus the square root of 2 over 6. Or I like this better, square root of 2 minus 1 over 6. Either way. Hold up. Okay. Hold up where? Oh. Hold up with the gloating, not hold up with the problem. Do you have any questions there? Your cereal's still crunchy. All right. We good with that? No questions? Ready to move on? We're going to integrate sine cubed x times cosine x dx from 0 to pi over 6. What do you think we should let u equal? Sine of x? Okay, let's see what happens. So then du is so that I can rewrite this as u cubed, and cosine x dx is du. If x is 0, then u is sine of 0, which is 0. If x is pi over 6, then u is sine of pi over 6, which is 1/2. Again, changing from our x values to our u values made them easier to work with. Instead of working with 0 and pi over 6, now we're working with 0 1/2. Antiderivative of u cubed would be u to the 4th over 4, evaluated from 0 to 1/2. And because that dividing by 4 is basically the same thing as multiplying by 1/4, I'm going to go ahead and factor out that 1/4, plug in my 0 and my 1/2, and then we'll multiply it at the end. So I have 1/2 to the power of 4. Well, 2 to the 4th is 16. So that's 1/16. By the way, whenever I have a power of 4, I try to break it down into a power of 2, right? Because if you think about it, u to the 4th is the same thing as u squared squared. I think it's easier to square numbers than try to figure out the 4th power. So I don't think of this as 2 to the 4th. I think of it as 2 squared squared, as 4 squared, 16. Does that make sense? Minus u to the 4th, 0 to the 4th would be 0. So I have 1/16 times 4, 64. That's a funny face you made about the music. It's not English. I'm confused. This isn't English. Do you guys have any questions about this one? Again, I didn't have to pull out this 1/4, but if I hadn't have done that, I would have had 1/16 divided by 4, and then I would have had to have done a little bit of manipulation with fractions. So I think that a lot of times, especially when the constant is a fraction, if you pull it out and work with the rest of the stuff and then multiply it back at the end, it's a little bit easier. That's just a trick that I use. Okay, let's look at the next one. This one, they want us to find the area bounded by the graph of y equals x times the square root of x squared plus 1 and the x-axis on the closed interval from 0 to 2. So they've given us the graph. We're looking for the area between 0 and 2 in the x-axis. So that area. And we know now that if we're looking for area, we should be evaluating a definite integral. So the area will be equal to the integral of x times the square root of x squared plus 1 with respect to x, starting at x equals 0, stopping at x equals 2. So it looks like we're going to have to do a little U-substitution here. Let u equal x squared plus 1. Okay, so then du is 2x dx. We need the x, we need the dx. We don't need the 2, so we'll move it. You guys getting better at U-substitution? Like I said, it's in the beginning, it's something you have to kind of work a little bit on, but the more you do it, easier it gets. You guys have not had any problems using or picking the right u value right away. So then I've got the integral of u to the 1/2 times 1/2 du. If x is 0, then u is 0 squared plus 1. I am if I put the right bounds. With the right bounds, that's technically correct. So my lower bound is 1. U of 2 would be 2 squared plus 1, 5. So I have 1/2 times the antiderivative of u to the 1/2 would be u to the 3/2 divided by 3/2 or times 2/3. So I have 1/3 times u to the 3/2 evaluated from 1 to 5. I'll leave out the 1/3 for now. So I have 5 to the 3 halves. Well, that's saying take the square root and then cube it. No, what's the square root of, 125 would be the cube, but then what's the square root of that? Right? And the easier way to do it would be, well, what's the square root of 5? Well, it's just the square root of 5. It's irrational. So we can't define that any more precisely than that. Let's just leave it that way. Minus 1. I'll just leave it like that. Done. Unless I need to simplify that for some reason to match a multiple choice question, or if I need to get a decimal approximation. If I have a calculator, I could do that. Otherwise, I just leave it that way. Any questions about that one? All right, I want to go ahead and start discussing the next one, but I'm going to let you guys try finishing it up on your own. It uses some of the old concepts that we've talked about previously. It says that water is being pumped into a tank at a rate given by R of t. The table of values for R of t is given. They want us to use the data in the table and 4 subintervals to find a left Riemann sum to approximate the integral from 0 to 20 of R of t dt. And then they want us to do the same thing with a right Riemann sum. Now, I want to talk about what this represents if we're integrating this. We are taking a rate of change. And we talked about this at the beginning of this unit. If I integrate the rate of change, what am I going to find? Well, if we're talking about rate of change as velocity, we would find that. But here we're talking about the rate of change of what? Of the volume of water in the tank. So if I integrate the rate of change of the volume of the water, then I'm going to find the area, which represents what? If I integrate rate of change, I find amount of change. In other words, if I let W represent the volume of the water in the tank, then R of t represents the derivative of W of t. All right, we'll pause for the pledge. So if I integrate R of t, the integral of R of t from 0 to 20 is the same thing as the integral of W prime of t from 0 to 20. And according to the fundamental theorem, that's equal to W at 20 minus 20. W at 0. The amount of water in the tank after 20 minutes minus the amount of water in the tank at 0 minutes, which verifies what we just said, what we had talked about before. If I integrate the rate of change, I'm finding the difference in the volume. I'm finding the amount of change. Do you guys see that? So this represents the total change in the amount of water. All right, so I'm going to let you guys finish that, and we'll talk about it on Monday. This is reviewing left and right Riemann sums. So we know what it represents. See if you can find those approximations.